In mass spec, what is the name used to describe the ion that comes from knocking an electron from a molecule? Okay, well, the base peak, this is the peak that has the highest intensity, not the one that is for the molecule. A fragment is just something that results from the breakdown of that ion. An analyte is something that you're going to analyze, and so that's not what we call this ion. The parent peak is what we call this. Another term that we use is the molecular ion. What do we detect in mass spec? Well, it's not the energy of a molecule, although it will take energy to ionize a molecule, and we use the energy of a magnetic field to deflect the ion. We're not measuring the energy of the molecule. We also aren't measuring the number of electrons ejected. We eject an electron, but we don't measure how many. We just eject one and then do a detection on what is results. It's not the number of electrons needed to ionize a molecule, because you knock out one electron, it's an ion. You knock out two, it's an ion. That's not a valid measurement. The number of hydrogen atoms in a molecule, well, we can figure that out from a mass spec, but that's not what the purpose, what we actually measure in mass spec. The thing that we measure is the mass of the ions that are produced from ejecting an electron from a molecule. It forms both molecular ion and fragments, and when it's shot into the magnetic field, we're actually measuring the mass to charge ratio. Although, as far as we're concerned, every single ion just has a +1 charge, but it can't have a +2 charge. Then you have the mass is halved in relationship to the charge. So it is the number of ions. We're actually measuring the frequency of the ions produced of a particular mass to charge ratio. High resolution mass spec allows one to determine the molecular formula of a molecule, yes or no? Well, in regular mass spec, the mass of the molecular ion allows us to figure out possible, and usually several possible, molecular formulas. But when you use a high resolution mass spec, it narrows it down to only one possible formula. So this is true. High resolution mass spec would allow one to distinguish between the following two molecules, yes or no? Well, if we look at these two molecules, they have the exact same formula. All they are EZ isomers. In mass spec, the high resolution part of it is used just to distinguish what is the mass of the molecular ion, and so to get a specific formula. The specific formula would be the same for either of these, so it would not resolve this. The issue is is it an E or a Z isomer? In fact, even the fragmentation pattern would produce the same ions, and so it's doubtful you would see a difference between these two. If you did see a difference between the mass spec, it would only be in the intensities of the ions that are formed, and even then it would be a very minor difference. So it's false. High resolution mass spec gives a formula. It's not going to distinguish between cis and trans. which of the following isomers would you expect to produce a peak at the molecular ion minus 18? Well, all of these would produce molecular ion of minus 15 for the methyl, right here, minus 15, right here, minus 15, right here, minus 15, but this would not produce minus 15. We're looking, though, at minus 18, so the loss of a mass of 18. Mass of 18 should ring a bell of water for you. Which one of these can eject water? Alcohols can pluck a hydrogen off a nearby atom and form a water molecule and an alkene carbocation. So alcohols, sometimes you'll see a fragment which is made by the loss of water. So this is the one that we would see from the loss of mass of water. Okay, which one of these is the reason why some peaks are larger than others in a mass spec? Well, if we look at the peaks that we see in a mass spec, what are they due to? They are due to the formation of fragments when the molecular ion decomposes. Why is it that you make some peaks other than others? Well, when it decomposes, it tends to go to things that are more stable. So when it tends to go to things that are more stable, that's going to happen more frequently than an unstable cation that might be formed. So if I go and I look, the larger peaks represent fragments that are more stable. This is true because they're more stable, so they're more likely to be formed. So the correct answer to this is the first. Which one of these is most likely to undergo a McLafferty rearrangement? Well, a McLafferty rearrangement always results from a carbonyl compound. So you can eliminate all three of these. Cyclohexanone, and this would be heptanone, 3-heptanone. These are both have the possibility for a McLafferty. Let's look and see which one can really do it. For a McLafferty to occur, you have to have a carbon that is 3 away with a hydrogen on it. So it can make a 6-membered ring, hydrogen bonding over to the oxygen. There is no carbon that can come up this way on cyclohexanone, and so this cannot do a McLafferty. If you look at this ketone on this side does not have a carbon here that can put a hydrogen here. It has to be on the 1, 2, 3 carbon, having a hydrogen that can come over here. And so this side can't do a McLafferty. What about this side? Well, this can flip up. If it flips up 1, 2, 3, this carbon will be able to put its hydrogen over to hydrogen bond to this oxygen and allow the pericyclic reaction to occur. When that occurs, what would happen is the cleavage would occur here, giving the loss of all of this. If we look at a molecular vibration, a bond that is vibrating, if the wave number needed is higher to stimulate it, that means the energy of the infrared radiation absorbed is lower. Is this true or false? Well, wave number is inverse, the speed of light divided into the frequency, or 1 over the wavelength. The wave number directly correlates with the energy of the light. So if the wave number is high, the energy will be high. Which of the following types of electromagnetic radiation has the highest energy per photon? Well, if we look at this, radio waves are very, very low energy. They have very long wavelengths, and the only amount of energy that radio waves can do is basically make a nucleus flip its spin, which is an incredibly tiny amount of energy. Microwaves are next in energy level. These have the ability to take a water molecule and make it tumble faster. If I look at infrared radiation, this is the light that causes a bond to vibrate more. Visible light will take a very weak bond and break it. It's a very weak pi bond and break it. UV light will take a stronger pi bond and break it. The highest energy here is actually ultraviolet light, and that is the reason why going out in the sunlight and absorbing ultraviolet light, or going and sitting in a tanning bed and absorbing ultraviolet light, actually can cause cancer, because the energy is relatively high and it can do damage to the molecules in your body. Particularly of concern would be DNA damage that could lead to cancer. Infrared spectroscopy is based on what type of excitation? Infrared spectroscopy is based on the excitation of the vibrational modes of bonds. And so the answer here would be number 4. Which functional groups would we expect to make absorbances in the IR spectrum at 2200 approximately and 1650 approximately? Well, if we look at this, this is below the carbonyl. A carbonyl will not go this low. So this is a carbon-carbon double bond. So it could be either an aldehyde and an alkene and an alcohol, or an alkene and a nitrile. If I look at 2200, this is in that triple bond range. That triple bond range would either be an alkyne or a nitrile. So the only thing that would give you a peak here and here would be down here, the alkene and the nitrile. If you have R2-pentanol and S2-pentanol, would they give the same IR spectrum? Fingerprint and all? Would they be identical? Well, if you remember back when we discussed chirality, what we said is that enantiomers have identical physical characteristics except for the rotation of light. Does infrared radiation involve the rotation of light? No. It's the absorbance of light in a vibrational mode. So the answer to this is these would have identical IR spectra because it does not involve chirality. It only involves vibrational modes. Okay, which of the following compounds will the carbonyl absorb at the lowest frequency? Okay, when we look at absorption of frequencies, strong bonds absorb at higher frequencies and weak bonds absorb at lower frequencies. What weakens a carbonyl? Well, those things that would pull the electrons away from the carbon-oxygen bond and put it somewhere else is what you would expect to see for weakening it. If I go ahead and I look at esters, esters have a resonance in which the electrons come down here, put, the electrons in the non-bonding pair come over here into this bond here, and these electrons jump up there and put a negative charge here, a positive charge here, and a double bond there. That resonance structure causes this double bond to be weakened under a two-bond evaluation. And so both this ester and this ester have resonance structures that weaken them, and so they would have lower frequencies. Neither of these two would have that problem. However, if I look at this carbonyl can be in conjugation with this double bond. That's going to be an even stronger resonance because a positive charge can be put here, the electrons here jump in there, and then these electrons jump up there. And putting a positive charge on a carbon is even better than putting a positive charge on an oxygen. Conjugation tends to put a lot of double bond strength between these, what would be considered a single bond there. If it's putting a lot of double bond strength there, this is weakened considerably. So this molecule right here has conjugation with a double bond that really weakens that carbonyl and puts double bond character here. This one is not conjugated. There's a methylene group there, and so it's not conjugated. And this is not conjugated, and there's no resonance structure with it. So this right here, this conjugated ketone, has the lowest frequency in an IR spectrum. Which of these frequencies ranges is considered the fingerprint region? Well, if I look at this right here is the region just above the oxygen-hydrogen bond. This is really very high, and it's unusual to find much in that range, except for maybe the broadness of an alcohol bringing it into there. Or sometimes you'll find nitrogen-hydrogen bonds up here. This is in that OH frequency and also in the carbon-hydrogen area. This takes from carbon-hydrogen area down into the double bond area. Right here, this would be double bond to a carbonyl double bond and a double bond area, carbon-carbon double bond area. And then this range right here, that is the fingerprint range. Will E2-butene and Z2-butene give identical IR spectra? Now remember, these are not chiral compounds, but this is basically cis or trans. Cis or trans double bonds actually have differences in dipoles, so the intensity of the carbon-carbon double bond would be different between these two. And not only that, the vibrational modes are going to be different when you have bonds on the same side and bonds on the opposite side. So no, they would not have identical spectra. They would be similar, but definitely not identical. Can you suggest a structure for this? This may take you a little time, so pause the lecture and do a little work on this, see if you can figure it out. Okay, first thing, go to the mass spec and look at the molecular ion. What does that tell you? See, this is 30% of this, and it's M and M plus 2. This is an isotope signature. Likewise, if I take 90 and subtract out 55, what do I get? I get 35. If I take 92 and subtract out 55, I get 37. These are the masses of the chlorine isotopes. The IR spectrum tells you something about the functional groups also. If you look right here, we can see that we've got a double bond. This is a carbon-carbon double bond. It's not high enough, not up here, where you see the carbon-oxygen double bond. And not only that, it's not very intense. And that kind of helps confirm that it is a carbon-carbon double bond. Also, notice over here, this peak is above 3,000. So what do I see? I see a carbon-carbon double bond in here. It's important to note there is no hydroxyl group here, and you don't see a carbonyl. This is not considered a carbonyl. It's probably an overtone for the carbon-carbon double bond. We see this right here. If it were a carbonyl, it would stretch way down here. That's not a carbonyl there. So we can say no hydroxyl group, no carbonyl. What do we have? A carbon-carbon double bond. And we also can see that we have some carbon-hydrogen bonds where the carbon is sp3. So these are alkyl groups causing this. The 92 and 90 peaks tell you have chlorine. And when the chlorine free radical leaves, you get this peak of 55. So 55, how many carbons is that? If you divide 12 into 55, you get 48. So the maximum number of carbons it could be is 4. If you have 4 carbons, what's left over? 7 AMU. That would be 7 hydrogens. This is giving us a probable formula that's C4H7 chlorine. This is 1 degree of unsaturation, which makes us feel more comfortable with that carbon-carbon double bond. If you look at the 75 right there, that 75, that's a pretty small peak, but if I look at 75 from 90, that's 15. That's probably the loss of a methyl. Why is it so small? Because the loss of chlorine is so high. That's what really wants to happen as a chlorine radical flies off. But sometimes a methyl group is flying off. It's just not as likely as that chlorine free radical to fly off. So what can we conclude from this? I'm going to say a good possibility is that you are having this structure for this spectra. Now, you can't decide, just with the mass spec and the IR that this is for sure the structure. We have another type of spectroscopy that we're going to start learning about that would confirm this or refute it. And then you could go back and you could try to deduce what the structure is from the information here and from that other type of spectroscopy.